I had just mentioned Barnard's star, which is the second closest star system to us. Anyhow, it actually has what's called proper motion, and it shifts its position in the sky not because of parallax, right? Of course, it shifts its position in the sky because of parallax, but it actually moves with respect to the background of stars. It does this over a very, very long period of time, but we've been observing this star for many, many years now, and over time it shifted its position, and so we can actually measure what's sometimes it's called the transverse velocity, or an idea would be like if you're just looking at a picture, right? Let me get this cursor over here. So we could measure the velocity going perpendicular to ourselves. Of course, we can get what's called the radial velocity. That is, if this star is moving towards us, we can measure, or away from us, we can measure that with the Doppler effect. But what about perpendicular velocities? And see, the thing is, we can actually measure that with some of the very closest star. And Barnard's star actually happens to have the largest proper motion or transverse velocity that we can measure. I mean, I'm sure there's plenty of stars out there moving faster than Barnard's star. I know that there are, but they're too far for us to actually see that. There's actually programs that I've looked at over the years that will, for example, it'll show, let's say, like the Pleiades, right? The Seven Sisters, which is a collection of many hundreds of stars actually. And if they're like programs, simulations, and what they do is they will show what the estimates of the proper motions and the radial motions put together, and they'll basically show, for example, how the Pleiades will move. The stars will move with respect to each other over the course of hundreds of thousands of years. Even the constellations, right, that we take for granted that they're always there and they always look exactly the same, and they do, certainly in recorded human history, which is roughly 10,000 years. The night sky, what we can see as far as the stars go, has never changed. Not in that that brief period that we have of recorded history, about roughly 10,000 years, as I mentioned. But if you go back, 100,000 years, and then maybe 200,000 years, the positions of the stars in the night sky have changed with respect to each other. Again, it's very slow, but we can use this idea of proper motion and radial motion, which we've measured a lot of stars, certainly within our galaxy, many stars in other galaxies too, but that's a whole different story. But with these measurements, we can extrapolate what the positions of the stars will be in the future. All right. Anyhow, so that's our first step. All right, and so this is nice because this is showing you. For example, Alpha Centauri, right? If you look up Alpha Centauri, it looks like it's heading towards us. Okay, like if you Googled Alpha Centauri, it has a velocity in the direction of the sun. See, and that's only partially true, right? It's true motion, right? So this red arrow represents its true motion, and notice it's traveling at about 30 kilometers per second. And then, from the Doppler, okay, so that's not something that is observed directly. All right, I want everybody to understand that you don't measure this directly. What you do is you measure the radial velocity, which turns out to be about 20 kilometers per per second, which you can do with the Doppler shift. Notice it's blue shifted because it's moving towards this. That part of its motion is moving towards the sun, and so we can also see that it's also has its own proper motion, and so when you combine the two, like this this leg right here of a right triangle, right? This is the transverse motion. This side of the right triangle is 24. This side of the right triangle, which is the same as the radial velocity, is 20. From the Pythagorean theorem, you can actually work out what the actual or true speed is, and with a little bit of trigonometry, you can work out what this angle is as well. All right, so we know that it's not this Alpha Centauri, or the system itself, the three stars that make up the Alpha Centauri system, is not really moving towards the sun at all. It's not going to collide with the sun, never. Okay. All right. So let's move on. All right. So let's think about luminosity, or as it says here, the absolute brightness. It's a measurement of the total power. Remember, power we measure in watts. Sometimes we'll use those terms, power and energy, interchangeably, but really they're not the same thing. The difference is power is energy per unit time. But if you think about how much power in 1 second, then you're talking about energy. And by the way, energy, when you talk about energy, it's usually measured in units called joules, right? So, like for example, 1 watt is 1 joule divided by 1 second, one joule per second. All right. So keep in mind, like for example, the luminosity of our sun, which I think there's a couple of slides forward that shows this, and we've talked about this before. It's about 4 times 10 to the 26th, right, watts. All right, so that's the amount of it's kind of like measuring the power of a light bulb. How much, like a 100-watt light bulb or something like that. A 60-watt light bulb. The apparent brightness is how bright the star appears when you look at it from Earth. You look out into the night sky. How bright does it appear? Of course, the brightest star in the night sky is called Sirius. Its magnitude, by the way, its apparent brightness. We'll talk about magnitude in just a moment, but its magnitude is actually in the negative region. I think it's like something like negative 1.4 or something like that. I'd have to look it up exactly what the brightness is, or what the apparent brightness is. All right, and then what we want to do is looking at finding the apparent brightness is fine enough, but we'd like to know what is the brightness on an absolute scale. Like if you take away the idea of distance, of course, objects that are emitting light are going to appear brighter when they're closer to us than when they're farther away, of course, because of this, the inverse square law, right? This is an example of the inverse square law. There was a lab on this, of course. So the energy flux, the amount of the number of watts per square meter is decreases as the square of the distance. That's what this equation is talking about. All right, so this absolute brightness scale, as we're going to see, basically eliminates well, that doesn't eliminate it, but it basically mathematically, okay, it's important to understand this, it's mathematically putting all the stars at the same distance away. And how bright would they appear? Right, so that would get away from this idea of apparent brightness, because again, it depends on how far away they are, and also how luminous the star truly is. And see, this apparent brightness would tell us how luminous the star truly is. All right, we'll get into that in a little bit. And by the way, what we do mathematically is we put all the stars at 10 parsecs away. That was the agreed upon distance long ago. All right, so anyhow, so as I was just mentioning this, so two stars in the night sky could appear the same brightness, but if it turns out that one of them is much further away, and with the nearby stars, we can measure the distances using the parallax method, using trigonometry and using the Earth as a baseline, or the Earth's orbit as a baseline. If the stars that are if they appear both the same brightness, but one of them is further away, the one that's further away would of course be truly the brighter star, right? Because it's going to, when you talk about another star being further away, it's going to be much further away, right? Remember, stars are spaced apart. In our part of the galaxy, every few parsecs. All right, so let's see. So the luminosity and the apparent brightness. So apparent brightness is apparent luminosity is the measurement on a magnitude scale, which is related to the human eye. It turns out that the human eye puts this magnitude scale. Just to remind everybody, we talked about this in you might have already heard me talking about this, but the magnitude scale, first of all, is backwards, right? In the sense that lower numbers are brighter stars, and then dim stars are higher numbers. For example, a seventh magnitude star, which you can't see with the unaided eye, you need a pair of binoculars or something like that, or even a small telescope to be able to see a seventh magnitude star. That is, that's a dim star. But then like a second magnitude star, you can just look up in the night sky and see that very easily with nothing else but your eyes. It turns out that Hipparchus, who was the guy that came up with this magnitude scale, didn't realize exactly how bright stars truly are, and the scale now extends into the negative region, as is indicated, right? Let's see. So take a look at this. Like, for example, there's Betelgeuse, Polaris. Notice Polaris is actually not a particularly bright star. It's about 2.5. Remember, the human eye can see to about the 6th magnitude. So, for example, Barnard's star, which is a 9.5, you could barely see that with binoculars, right? I mean, you'd have to have a pretty good pair of binoculars to actually be able and know exactly where to look to see that. They're serious. They're saying it's about 1.5. Negative 1.5. So notice it's below. So like a 0th magnitude is a very bright star, but there are stars like Sirius. Well, there's very few of them, but on the absolute scale anyway, that are brighter than 0. So Sirius is a negative. I think it's actually technically a negative 1.4. And there's another star called Canopus that I think is the 2nd brightest star in the sky. I think that one is also negative. I'd have to look that one up as well. Notice Venus at its brightest, and Venus's brightness changes because it actually exhibits phases, and when it's further away from us, it actually looks dimmer. But at its brightest, Venus can be as bright as a negative 4th magnitude. The full moon is greater than a negative 10th magnitude. The sun is about more than negative 26th. So that's of course something so bright it lights up the. It's so bright that it blocks out the light of all the stars in the night sky, or in the sky, I should say, really. 'Cause remember, the stars are always there, but the sun is just so bright we can't see them. That's why it's really amazing that you can see the stars when there's a solar eclipse. I mean, you realize, oh, yeah, that's right.